Okay. Okay, some of the applications that we can use graphs for include those that can build a tree out of a set of related items. Now, say for argument's sake, you were starting a new cable company and you wanted to plan your cabling infrastructure. You know that your base station would have to be connected and you'd have to connect all the other clients that would be in the area. Now, one way of doing that would be to do something like a depth first search. And if you do a depth first search, you could actually get a tree. And that tree would actually span the graph, so we could call it a spanning tree. Now, since you're running cable, you may realize sooner or later that the wires are very expensive. So you really would want to make a tree that spans the graph and has the minimum weight. So a minimum spanning tree would be useful. Now, we really didn't go too much in detail with the MST algorithms except to describe two of them that are commonly used. One is Prim's minimum spanning tree algorithm, which starts from a certain point and then looks around that certain point for the edge that is lightest. And once it, of course, while it's looking around, it adds all the candidate edges. Now, it moves to the lightest, to the node that's on the other end of the lightest edge, and then looks around from that. Now, once it finds the node that has the lightest, that is connected to the lightest edge, it keeps on adding to the tree the node that has the lightest edge until it adds all the nodes in the graph.
What's the lightest edge, sir?
What's that?
What do you mean by the lightest edge?
Oh, the
smallest weight?
Smallest weight. Frames will work on a weighted graph.
Okay.
So it keeps on moving to the edge with the smallest, to the node on the end of the edge with the smallest weight, until it adds all the nodes to the graph. At the end of that, you're going to have a tree that spans the graph, and that will be a minimum spanning tree. Now there's another strategy to build a minimum spanning tree, and Couscous algorithm uses that strategy. What they do is take a list of all the edges and they sort them, and once they sort them, they then put the edges back out on the graph in ascending order of weight. So once they've done that, then they'll get every single node connected in the graph. Once the graph is connected that you had started with. Alright, so we won't look at an example of that because of the limited time, but I think it's important for you to understand what the time complexity of Couscous algorithm would be. If you're going to, well, the first thing you're going to do is take a list of all the edges. A graph will normally have n nodes, and we normally use the variable m to describe the number of edges. So to take a list of all the edges would be a theta m operation. Now, if we're going to sort those edges, remember, if we're going to sort n items, the best we can do if we don't know anything about the data is theta n log n. If we're going to sort m edges, the best we can do is theta m log m. Now, the next step is to pull each one of those edges from the graph, from the set of edges that we have sorted, and add them back to our tree or spanning tree if we don't create a cycle. A tree does not have cycles. So the process of adding each edge back to the tree and checking to see if we create a cycle can be done pretty quickly with this algorithm called the union find algorithm. We won't go into the details of that, I think it's in the textbook. But an important thing to note is that that algorithm runs pretty fast. The time complexity is log star m. Again, we won't go into details of that. You can look that up. But log star m is so fast so that for all intents and purposes here, we can consider it a constant time algorithm. Now, once we add those times together, we're take the list of edges theta m, sort the edges theta m log m, and m of the adding back to the tree. So that's another theta m operation. So the whole time complexity of Couscous is theta m log m. Now, creating a spanning tree is just one of a set of algorithms that we can use. Another commonly used algorithm is to get the shortest distance from one point to any other point. And there's an algorithm called Dijkstra's algorithm, Dijkstra's single source shortest path algorithm, that works very similar to Prim's MST algorithm. The only difference between Dijkstra's and Prim's is that while you have visited a node, you're going to now look for the edge with the lightest weight, and you're going to be navigating to nodes at the end of the edges with the lightest weight. But in determining your weights, you then add the distance you've traveled to get to that node that you're going to be looking from. So there are examples that you can look at. We won't look at them right now. And that's it for graphs if we have no more questions. Okay. Now, the last thing we have to just take a quick look at are the concept of whether or not something is easily computable or hard to compute. We've been looking at some algorithms, and most of them have had polynomial time execution. We've seen our theta n operations or theta n squared operations, and we can have theta n cubed operations. But a lot of the real world algorithms may actually fall into other classes. Now let's take an example. Suppose you wanted to actually drive around the island. You are a salesman, and you wanted to be very efficient. Now you have your map, and you wanted to drive through all the towns in Jamaica, visiting each town only once, and then end up back at your base. Is there a way to do it? How are you going to find that out? What's that?
I'll plot it out on the map.
Well, there may be about 1,000 towns in Jamaica. How long would it take you to plan that route?
A long time.
Well, a lot of these problems fall into a class where if you know the answer, if you know exactly what the route is, then you can say, okay, the time will take that a certain expression. But if you don't know, then it may take you a long time to figure out whether or not it's there or not. I mean, the answer for what you're looking for is actually there. So basically, these questions like that fall into one or two classes. You have what we call a decision problem or optimization problem. In the decision problem, the question is whether or not there is a solution. In the optimization problem, the question is whether or not you can get an answer that is better than a certain answer. For example, you could actually have an optimization problem for that same problem where you're driving around the country and trying to figure out what's the best way. You could say, can I do it and travel less than so and so miles? Okay. So that's a question that you can ponder in your mind. Now, the complexity class P describes all the problems that we know that we can solve in polynomial time. There's also another complexity class called NP, and that's reserved for algorithms that includes the algorithms that are in complexity class P. Because the way you normally solve the problems in NP, or one way of solving problems in NP, is to guess the answer, and if it's right, you're good. So if you know the answer already, then you can solve it. So if you had some magic answer generator that could actually just throw the answer, then everything that you would have to work out would have been be able to be solved in the same time as the things that you could have solved in polynomial time. So in short, P class of algorithms in polynomial time. Now, if you have a non-deterministic algorithm, then you can actually resolve that. You can actually resolve the solution to a problem in polynomial time. It's not working. So now, as I said, in a non-deterministic algorithm, you guess the answer and then you can check it in polynomial time. But the importance of recognizing these different computability problems is that there are some problems that are considered to be hard. For example, cracking the RSA code. Now, cracking RSA is really dependent on you figuring out whether you can factorize some primes. If you have some large primes multiplied, then you can figure out the primes and then factorize them, then you can crack RSA. Now, because the computers that we have would only try a certain strategy that would take a very long time to actually solve that, maybe longer than you and I would live, then RSA is considered safe. However, if there was a way to actually generate a solution to that hard problem in an easy time, in a quick time, then RSA would no longer be safe. And it's actually an ongoing debate whether or not there are easy ways to solve these hard problems. So if you actually search on the internet, the question still stands: is complexity class P, where that describes the things that we can solve in polynomial time, equal to the complexity class NP, which describes the harder set of problems? Alright, we're out of time. We actually needed more time to actually fully discuss this, but I think we're going to stop here.